Lesson 12, Magnetic Forces and Circular Motion. If a magnet is placed in a magnetic field, it will experience a force, either repulsive or attractive, and the direction of this force depends on the type of magnet you're using. A permanent magnet is a magnetic substance found in nature, usually either nickel or iron, that contains magnetic properties and can't be turned on or off. An electromagnet is a magnet that's produced by the movement of charged particles. This can be either a single moving charge or a wire that is carrying current. An electromagnet can be turned on or off. The direction of the force on a permanent magnet in a magnetic field depends on the direction of the magnetic field itself. A north pole is experiencing a force with the field. A south pole will experience a force that is opposite to the direction of the field. For an electromagnet, determining the direction of the force on the magnet is a little bit more complicated. You need to use the third hand rule. The third hand rule is used to determine the direction of the magnetic force on a charged particle moving in a magnetic field. For the third hand rule, use your left hand for negatively charged particles, or the flow of electrons through a circuit. Use your right hand for positively charged particles, or conventional current. To do the third hand rule, you place your fingers and your thumb so you make an L shape between your thumb and your fingers. You point your thumb in the direction of the particle's velocity. You point your fingers in the direction of the magnetic field. The force on the particle is directed out of the palm of your hand. Example 1. For a magnetic field into the page, what is the direction of the force on a proton initially traveling to the right? Since we are working with a proton and protons are positively charged, you use your right hand for the third hand rule. Point your thumb in the direction of the proton's velocity. Your fingers point into the page in the direction of the magnetic field. The force comes out of your palm, directed upwards. So again, your thumb points in the direction of the velocity. Your fingers in the direction of the magnetic field. The palm of your hand indicates the direction of the force, which is up towards the top of the page. Example 2. A current-carrying wire is placed in a magnetic field directed upwards. What is the direction of the magnetic force on the top section of wire? The battery symbol is drawn, so the positive terminal of the battery is the longer side of the wire. The current is drawn so that the current comes out of the negative end and goes into the positive end. This tells us that the current that we're looking at in the diagram is electron flow. In the top section of the wire, the electron flow travels to the right. Since we're working with electron flow, we want to use our left hand for the third hand rule. So we point our thumb in the direction of the current and our fingers in the direction of the magnetic field. Our palm points into the page, which gives us the direction of the force. Again, thumb goes in the direction of the current because that's the direction of the electron's velocity. Your fingers point in the direction of the magnetic field. And your palm points into the page, which gives us the direction of the force. Example 3. A proton and an electron are placed into a magnetic field directed into the page. Particle A experiences an upward force and particle B experiences a downward force. Which particle is the proton? To solve this problem, we're going to use both hands to figure out which particle corresponds to the right hand or the positive hand. Starting with the left hand, we point our thumb in the direction of the particle velocity, our fingers into the page, and the force comes out of the palm. This eliminates particle A, which is forced upwards. Checking with our right hand, particle B. Right-hand thumb goes in the direction of the particle velocity, fingers into the page. The force ends up downwards, which tells us particle B is the proton. So with our right hand, when we point our thumb in the direction of the particle's velocity, which is to the left, our fingers in the direction of the magnetic field, which is into the page, the palm of our hand ends up pointing downward, which tells us particle B is the proton. So far, we know how to get the direction of the force on a charged particle traveling in a magnetic field. The direction is given by the third hand rule, where you point your thumb in the direction of the particle's velocity, your fingers in the direction of the magnetic field, and the magnetic force comes out of the palm of your hand. The magnitude of this force is given by the formula Fm equals BQV, where Fm is the magnetic force, B is the magnetic field strength at that location, Q is the charge of the particle traveling in the magnetic field, and V is the velocity of that particle as it travels through the field. Note that this formula only works if the velocity is perpendicular to the magnetic field. This is one of the rules of the third hand rule as well. The magnetic field and the velocity are always perpendicular to each other in order for the third hand rule to give you a proper direction. If the velocity is not perpendicular, you must calculate the perpendicular component first and use it instead. We'll start with an easier example. Example 4. An electron has an initial velocity of 9.1 times 10 to the 4 meters per second to the left when it enters a magnetic field of 1.1 times 10 to the 2 teslas into the page. What is the force on the electron as it enters the field? We'll start by determining the direction of the electron in the field. Since it's an electron, we use our left hand for the third hand rule. Point the thumb in the direction of the electron's velocity to the left, and our fingers into the page in the direction of the magnetic field. The magnetic force comes out of the palm of our hand and is directed upward. So we know the direction of this force is upwards towards the top of the page. To calculate the magnitude of the magnetic force, we use the formula BQV, where B is the magnetic field, which is 1.1 times 10 to the negative 2 teslas. Q is the charge of an electron, which is 1.6 times 10 to the negative 19. You'll notice I didn't put the negative sign in for the charge, even though we know electrons are negative, because we don't want to confuse the negative with direction. The velocity of the electron is 9.1 times 10 to the 4 meters per second. This gives us a magnetic force equal to 1.6 times 10 to the negative 16 newtons, and we put our direction that we found from the third hand rule in there, which is direction up. Example 5. An electron has an initial velocity of 1.9 times 10 to the 5 meters per second at an angle of 20 degrees south of west when it enters a magnetic field of 2.4 times 10 to the 3 teslas directed north. What is the force on the electron as it enters the field? Now the formula Fm equals BQV requires that the velocity of the particle in the magnetic field is perpendicular to the direction of the field. To solve this problem, we have to separate the electron's velocity into its x and y components. We can see that the x component, which is pointing west, is perpendicular to the magnetic field. The y component doesn't interact with the field at all, so we entirely ignore it when we're solving this problem. The x component of the velocity is given by the velocity times cosine of 20. So the electron's velocity in the x direction is equal to 1.785 times 10 to the 5 meters per second in a direction west. Next, we're going to use the third-hand rule to determine the direction of our electron's force as it travels through the magnetic field. Since it's an electron, we want to use our left hand. For the third-hand rule, we point our thumb towards the west in the direction of the electron's velocity. We point our fingers towards the top of the page or north in the direction of the magnetic field. The magnetic force is given by the palm of our hands, and the force points out of the page. So the direction of this force is out of the page, or upwards. The magnitude of the magnetic force is given by BQV, and this is the magnetic field, 2.4 times 10 to the 3 teslas, times the charge of the electron, which is 1.6 times 10 to the negative 19 coulombs, times its velocity, which is 1.785 times 10 to the 5. This gives us a force equal to 6.85 times 10 to the negative 11 newtons, and the direction we know already is out of the page. Example 6. An electron has an initial velocity of 1.5 times 10 to the 3 meters per second to the south when it enters a magnetic field of 1.1 times 10 to the 5 teslas to the south. What is the force on the electron as it enters the field? Let's start off by drawing a picture of what's going on. The magnetic field is directed to the south, and when the electron enters the magnetic field, it enters with an initial velocity that is also traveling to the south. Since the velocity and the magnetic field are parallel, the formula Fm equals BQV tells us that we have a 0 Newton force. There is no perpendicular component of the velocity. For this reason, the magnetic force is 0. As long as the magnetic field and the velocity of a particle point the same direction, there will be no magnetic force on the particle. Magnetic forces and circular motion. When a moving charged particle enters a magnetic field, it experiences a force perpendicular to its motion. We've seen this situation before. Whenever a particle experiences a force perpendicular to its motion, it starts to move in a parabolic or circular path. This causes the particle in the magnetic field to travel in a circular path. This is similar to the movement of a satellite around a planet, for example, the moon around the Earth. The moon always experiences a gravitational force directed towards the Earth, even though its velocity is continuously pointed perpendicular to this force. Let's examine this situation with a charged particle. In this example, we have an electron traveling towards the left, traveling through a magnetic field that is directed into the page. Since it's an electron, we'll analyze its motion with our left hand. At the beginning, the velocity is pointed to the left and the force is directed upwards. But as it follows this force, it starts to move in a curved path. So later on, once the velocity is pointed upwards, the force ends up pointing to the right. And it continues to follow this circular path, and as it follows the path, the force component continues to be pointed towards the center of its circular path. As a result, the charged particle will continue to travel in the original direction of motion, but in a spiraled path. It looks something like this, until it exits the magnetic field. Since the circular motion of the particle is caused by the magnetic force, we can use Fm equals Fc, where Fm is given by the formula BQV, And the centripetal force is given by the mass times the velocity squared divided by the radius of the circular path. Since the velocity appears on both sides of the formula, it cancels out once on each side. This gives us BQ equals mv over r. This can be rearranged in various ways. One particularly useful rearrangement is to solve for m, where m is BQ times r divided by v. Alternatively, you might want to find the radius of the path, where radius is mv divided by BQ. Example 7. A particle with a charge equal to the elementary charge enters a magnetic field of 14 teslas with a speed of 2.3 times 10 to the 6 meters per second. The particle moves in a circular path with a radius of 935 nanometers. Is the particle a proton or an electron? We start by writing down the equivalency. The magnetic force is equal to the centripetal force, where we have QV equals mv squared over r, where v cancels out once on both sides. Rearranging this for m gives us m equals bqr divided by v. So the mass of this particle is equal to 14 teslas times the elementary charge times the radius, which is in nanometers. So we write this as 935 times 10 to the negative 9, because nano is negative 9, divided by the velocity of 2.3 times 10 to the 6 meters per second. This gives us a mass equal to 9.1 times 10 to the negative 31 kilograms. And when we look at our formula sheet to look at the masses of various particles, we see that this is the mass of the electron. Example 8. An electron is accelerated from rest using a voltage of 200 volts before it enters a magnetic field of 0.15 teslas perpendicular to the field. What is the radius of the electron's path? This problem is a two-step problem. In the first step, we need to determine the velocity of the particle when it enters the field. To do this, we use voltage equals the change in energy divided by the charge of the particle, where the change in energy is the change in kinetic energy. Which is Ek final minus Ek initial. Since we know that the particle started at rest, this tells us there was no Ek initial, so the change in kinetic energy is just equal to the final kinetic energy, which is 1/2 mv squared. Don't mix up the v as in velocity and the v as in voltage. So we have voltage equals 1/2 mv squared divided by q, which tells us that the velocity is equal to 2qv divided by m square rooted. So the velocity equals 8.38 times 10 to the 6 meters per second. Next, we use this velocity in the circular motion formula to determine what the radius of its motion is. So the magnetic force is equal to the centripetal force, so BQV equals mv squared over r, where v cancels out once on both sides. This leaves us with BQ equals mv over r, which tells us r equals mv over BQ. So the radius is equal to the mass of the electron, 9.11 times 10 to the negative 31, times the velocity, which is 8.38 times 10 to the 6, divided by the magnetic field, 0.15 teslas, times the charge of the electron, which is 1.6 times 10 to the negative 19. This gives us a radius equal to 3.2 times 10 to the 4 meters. The Northern Lights is a really interesting example of how charged particles travel in circular paths through a magnetic field. When charged particles from the sun or solar wind spiral along Earth's magnetic field, the result is the northern lights. We also call this the Aurora Borealis. So as the sun shines, occasionally it emits a solar flare. Solar flare sends charged particles towards the Earth in the solar winds. As these charged particles hit Earth's magnetic field, they spiral along the magnetic field towards the poles. So people living along the poles can see the result of these particles as they spiral through the magnetic field, and they see it in the form of nice colored lights, or the northern lights.